Alright, so now we're going to start looking at the idea of the limit of a function. So we're going to start off with kind of a set of notes that are a little more informal, get kind of the feel for some of the notation and the way we talk about things, and then we'll get a little bit more precise in the next set of notes. So informally we say, we use the notation lim as x approaches a of f of x equals L. Now here, a and L are going to be numbers that we're using. And so we read this as saying the limit of f of x as x approaches a equals L. So what this really is trying to say that we can make the output values of f of x, or the y values, arbitrary close to L, as basically as close as we want, by taking x that is sufficiently close to a on either the left or the right. However, we're not actually looking at values that are equal to a. So basically we've got this function, we're trying to get x as close to a as possible without just plugging it in, and when we look at those values, it looks as though those values of the function are getting close to L, both when we come from the left and when we come from the right. So as an example, say we wanted to take a look at this graph on the left, f of x. So here we could maybe have this point over here. So say we wanted to look where x was equal to -1, and here our y value, it looks like, is 3. So here, when we take the function and we go towards the point on the graph from the left, it looks as though those y values get closer and closer to 3 as we get close to -1. And on the right, it also looks like we're getting closer and closer in our y values to 3 as x gets closer to -1. So here we could say that the limit as x approaches -1 of this f of x equals 3. All right, so that's what we're saying. We're saying that as we get closer, the values look like they're getting closer and closer to 3 for the y values. So as the x values get close to -1, y values get close to 3. So here, it's important to note that in this case, f of -1 actually is 3. But this isn't always what happens. So sometimes we have some sort of weird things where we've got a piecewise function, and so maybe we get some jumps, maybe we get some open circles that happen. So let's say we wanted to go ahead and look at the value for x equals 1 on this graph for what we're going to call g of x. So for g of x, if we wanted to look at the limit as x approaches 1, what we're doing is we're looking at what it looks like the y values are going to be as we get closer and closer. And so here it looks as though they're getting closer and closer to a y value of 1 when we come in from the left and from the right. And so here we would say that the limit as x approaches 1 of g of x is 1, because that's what the y value it looks like they're getting closer to. However, notice that g of 1, so if we actually plugged in 1, is not going to be 1. It's instead going to be 3. So this is the difference between the idea of having a limit versus just going ahead and plugging in the function value. So we talked about this idea that if we're coming from the left and we're coming from the right, we want to know what it looks like the y values are approaching. But we don't always get that what it looks like they're coming in and approaching on the left looks the same as on the right. So say I wanted to look at something where maybe this was my function. So I had this, and then I had this going on. Over here, say this is x is equal to 1, this is y is equal to 1, and this is y is equal to 2, then what's going on with the limit on the left-hand side might be different from the right-hand side. So let's give this a little bit more formal notation. So let's say if we want to take the limit of f of x as x approached a from the left, what we'll do is we'll put a little negative sign as an exponent and say that's equal to L. And so this is the limit of f of x as x approaches a from the left. And what that means is that, again, we're taking and trying to get our x values arbitrarily close to a on the left side of a, but not equal to a. And so here, for this graph, for this example, let's call it h of x. Our limit as x approaches 1 from the left of h of x would be 1. So note that this up here doesn't mean negative 1, it means approaching 1 from the left. So if we were, say, coming from this side of things. Now, of course, if we can approach from the left, we also can approach from the right. So here we would say the limit as x approaches a from the right we'll use a plus sign of f of x equals L. And again, this is just saying the limit as x approaches a from the right. And so we're making f of x arbitrarily close to L by taking sufficiently close x values that are close to a on the right-hand side of a, but are not equal to a. And so again, looking at this example, if we looked at x values on the right of 1, we got closer and closer, it looks as though the y values are approaching 2. So we would say the limit as h of x, or the limit of h of x as x approaches 1 from the right would be 2. So those would be the two different limits we would be looking at. So what you'll notice is that the left and the right hand limits don't necessarily have to be the same thing. And so this is actually a way of defining whether or not the overall limit exists. So just as a little bit of a side note, the limit of f of x as x approaches a exists, but it only exists if and only if both the left and right hand limits exist and are equal. Otherwise, we say that the limit does not exist. Which we will sometimes just note does not exist as DNE. I'd like to take a moment to say that this, two things. One, we would notate that as the limit as x approaches a of f of x does not exist. Another thing I would like to say is that if you haven't seen Mean Girls, so Mean Girls is a movie, if you haven't seen Mean Girls, watch it. Because they have a little bit of math stuff in there, and at one point they talk about limits not existing. So it's fun. Anyways, so as a bit of an example, let's say we wanted to go ahead and look at this graph, which we're saying is the graph of a function f of x, and we want to go ahead and find different limits as we go. And if they don't exist, we're going to write just our DNE, does not exist. I'd like you to take a moment to pause the video and see if, with how things are labeled, you can figure out all 12 of these limits. If not, that's okay, but give it a shot. All right, assuming you haven't thrown away your shot, we're going to go ahead and look at these different limits. So first we're going to start off with talking about when x is 5. So when x is 5, it looks as though we're approaching this y value of 2. And it looks like this part of the graph is filled in. So when our x values get close to 5 from the left, it would appear that our y values get close to 2. Similarly, when we look at our x values coming towards 5 on the right, our y values again get closer and closer to this 2. Now, since the left and right hand limits are the same, we see that the overall limit is going to be 2. And notice that there's no open hole here, so this is the function value that we're looking at. So f of 5 in this case would be 2. Okay, so pretty straightforward when we have all of our values defined. Now, let's take a look at when x is 6. So when we're looking at 6 from the left, it looks as though we're getting closer and closer to this y value of 4. So we can go ahead and say the limit as x approaches 6 from the left is 4. But when we're on the right and we're getting towards 6, it looks like we're actually approaching 6 as our y value. So we'd say the limit as x approaches 6 from the right of f of x is 6. But now notice that the left and the right hand limits don't agree with each other. So on either side, we're not getting to the same, we're going towards the same y value. So we say this limit does not exist. So when we're looking then at this graph, and we want to know what the actual function value is between these two, well, we're going to go ahead and look at which has the filled in circle, which in this case is 4. So if we have these different limits on the left and right, the whole thing doesn't exist, but we still can have our function value. All right, and last but not least, let's go ahead and look at the x value 4. So when we look at this x value for 4, when we're coming in from the left, it looks as though our y value is going to be 0. And when we come in from the right, it looks as though our y value is going to end up being 0. So overall, we would say that the limit, as we're getting closer to that point, is 0. However, when we try to look at our function value, it's actually an open circle here, and we can see that the function value filled in above it is actually going to be 2. So just a thing to keep in mind as we look at these different limits. Just because the limit is something doesn't mean the function value will necessarily be that as well. So sometimes we're going to have to go ahead and compute our limits numerically. Now, this should remind you of trying to go ahead and find those instantaneous rates of change from before. We want to go ahead and estimate numerically our limit, or state that the limit does not exist. So what we're going to do is, if we wanted to look at this limit, if we tried to go ahead and just put in our value 9, notice that we'd get 9 minus 9, which equals 0, which doesn't work. So what we'll do is we'll go ahead and try to come up with a way of looking at the different y values. So we'll talk about different values for x, and then what this f of x is, which is going to be our square root of x minus 3 divided by x minus 9. So we can plug in different values for this, and we have our way of going ahead and making kind of a table of this, or we can just plug it in ourselves. So say we wanted to do the square root of, so if we're trying to get towards 9, we'll pick values right above 9. So 9.1 could be 1, 9.01, 9.001, and this will help us see a pattern. And then below, some x values we could pick below would be things like 8.999, 8.99, and 8.9. So let's try some. So we've got the square root of 9.1 minus 3 divided by 9.1 minus 9. And so we get a value of, if we round to 4 decimal places, 1662. So we can do 0.1662. Now we can go ahead and grab what we had before and now make it 9.01. So now we have to replace all our 9.1s with 9.01s. So now we get 0.1666, and now we can go ahead and replace it with 9.001. Again, we just want to get a few points to see what it looks like we are trending towards. Put one too many zeros there. So now it looks like we're getting closer to 0.166, and then rounding would be 7. And so let's try from the other side. So now let's go ahead and do 8.9. So we're going a few out just so we can kind of see that there's a trend. So now we have 0.1671. If we add another 9, so that's 8.99 now. Looking at 0.1667, and if we add one more 9 just for good luck, we're now looking at 0.166, and it rounds up to 7 again. So it looks as though as we get closer and closer, so as our x values get closer to 9, our f of x values get closer to 0.1667. So then what we'll say is that the limit as x approaches 9 of the square root of x minus 3 over x minus 9 is approximately 0.1667. Okay, so now we've got kind of a way to approximate this limit from a numerical standpoint. It'd still be nice if we could go ahead and get an exact value, and we will be doing this in a way that doesn't require us to do the problem 6 times in the coming videos. So we're getting to that. All right. Now, we also can have limits that go towards infinity. So if we say the limit as x approaches a of f of x equals infinity, that's how we read it. And essentially what we're saying is that our function value increases without bound, or in other words, just keeps getting bigger and bigger and bigger and bigger and bigger as x approaches a. We also can have that the limit as x approaches a of f of x equals negative infinity And this just means that our function values are going to keep decreasing without bounds over and over and over and over and over again. So it just keeps getting smaller and lower and lower and lower and lower. Smaller might not be the right term because it's just kind of a large negative quantity. From a technical standpoint, when a limit equals plus or minus infinity, it does not exist. So then why do we even bother saying infinity or negative infinity if technically it doesn't exist? Well, in some cases it helps us go ahead and determine what the behavior of the graph is. So say, for example, that we had a function that had a vertical asymptote at x equals -4. And both of our limits from the left and from the right went ahead and went straight up. And so they got larger and larger and larger as things went along. Well, what we would say is that the limit as x approaches -4 from the left of this function would equal infinity. Our limit as x approaches -4 from the right would equal infinity. And so we would say that our overall limit as x approaches -4 would equal infinity. So we're going up, without bound, whether we're on the left or right side. Now we could also have something similar happen, but instead we could be looking at something where both sides go down. And so here, if they're going around this 6, we'd say the limit as x approaches 6 from the left of this function was negative infinity. We also could say that about approaching 6 from the right. And we could just say it about the function overall without having to say our left or right. So negative infinity, negative infinity. Now, just because we're going to infinity doesn't necessarily mean that we have to be doing the same thing on the left and the right. So we could have something where we're going down to negative infinity on the left and approaching a positive infinity on the right, or we could have something where the opposite is happening and we are going to a positive infinity on the left and a negative infinity on the right. So here, for this graph, we would say the limit as x approaches 2 from the left of our function is negative infinity. However, the limit as x approaches 2 from the right of our function would be positive infinity. And so that would mean, of course, that the limit overall does not exist. Whereas here, when we're looking at the left of -7 of the function, that'll be positive infinity. And here, when we're looking at the right, we're looking at negative infinity. So those values are going lower and lower. And then again, because the left and right limits would not be the same, overall we would say the limit does not exist. So as one more example of this, say we wanted to go ahead and look at the graph of f of x equals x plus 3 over x squared. We want to find the limit as x approaches 0 of f of x using the graph. So we know here, looking at just this, we could say that our domain would be when x is not equal to 0, Or a better way of phrasing that would be that our domain goes from negative infinity to 0, union 0 to infinity. And so even though we know that our function is undefined at x equals 0, we still can look at that limit as x equals 0. So this here in the center is a vertical asymptote. At x equals 0. And so when we look at our function values to the left and to the right of 0, we notice that the limit as x approaches 0 from the left of our function is infinity, and the limit as x approaches 0 from the right of our function is infinity. And so our overall limit as x approaches 0 of our function is infinity. So say we wanted to go ahead and take this and try to find that limit numerically. Well, what we can do is we can go ahead and plug in those different values that are close to 0. And so again, this time I'm actually going to go ahead and review the idea of trying to look at it through the calculator. So say we wanted to define our function. So here we say that our function f of x is x plus 3 divided by x squared. And so from here we can go to our second window and make sure it asks for what the values are, and then it is second graph, where we can clear out all the values and plug in values around 0. So we want things that are negative, so negative 0.1, negative 0.01, negative 0.001, negative 0.001, and then 0.001, 0.001, 0.001, and 0.1. So as we can see here, looking at these y values, these E6s and E8s essentially denote that value and then how many zeros are behind it, or things that are roughly 0. And so when we're closer to negative 0.1 and 0.1, we have some pretty good sized values, but they very quickly jump up in magnitude as we just go a little bit closer to 0. And so this would be a good way of kind of helping us see that those function values are going to just keep jumping up as we get closer to 0. So as x approaches 0, our f of x values grow without bound. As such, this implies that the limit as x approaches 0 of f of x equals infinity. In the next video, we'll get away from kind of doing this thing where we plug in a bunch of different values, and we'll see how we can go ahead and put in values for f of x and do some kind of tricks to see exactly what those limits should end up being in a more algebraic way.